Okay, in this video we're going to continue our look at rational functions, and this time focusing on discontinuities, holes, and vertical asymptotes for those rational functions. This first example says consider the function f of x equals 3 over the quantity x minus 4. Clearly there is a discontinuity at x equals 4, which is the root of the denominator. We cannot have this denominator be equal to 0, so if x is 4 that would force the denominator to be 0, and that wouldn't work out. We can't divide by 0. So it says graph this function. So if we put in a coordinate plane here, and based on our previous lesson, we know that there's normally a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0. And using that information and our transformations, we can determine that the vertical asymptote should be moved right 4 because of that x minus 4. When we're with x, it's left and right opposite of the sign, so that's moving the whole graph to the right 4. That's the main transformation that's taking place, so the graph would fit in here like this. That would be what it would look like. So the question is posed, can we always conclude there are always vertical asymptotes at the roots of the denominator of any rational function? And that is a no. We're either going to have a vertical asymptote there, or we're going to have a hole in the graph, and we're going to be looking at what causes a vertical asymptote versus what causes a hole. We can analyze the function with calculator tables so as to understand when we have a vertical asymptote or when we have a hole in the graph. So, example 1, create two calculator tables to analyze the function values of f of x equals 3 over the quantity x minus 4 as x approaches 4 from the left and again from the right. So I'm going to make those tables and paste those in, and we'll discuss them. Alright, so I used my calculator to create these two tables. I just changed the independent variable to ask in the table setup and typed in values to make these tables. So notice in this table x is approaching 4 from the left side. It's at 3.8, 3.99, it's getting, and then 3.999, etc., getting closer and closer to 4. So that's actually this section of our graph above. And then in this table we're approaching 4 from the right hand side, so it's like we're going back this way following the graph. So we're getting closer, it's this section, getting closer and closer and closer to 4 from the right hand side. So I'm denoting that with this setup here as x approaches 4 from the left. That's what that means. This right here that I wrote, x approaching 4 from the right, that's what that means. And what we notice is that the f of x values here are approaching negative infinity in that table and positive infinity in that table. So negative infinity here, it's the y values, the f of x values drop to negative infinity there, and they're racing up to positive infinity here. So that's what we're noticing. So we can write that this way: f of x approaches negative infinity for that table, and then f of x approaches positive infinity for this table. So as x approaches 4 from the left, f of x approaches negative infinity. At here, as x approaches positive 4, f of x positive 4 from the right, that's what this is saying, f of x approaches infinity. So continuing on here, it says we already know from the graph above that there's a vertical asymptote at x equals 4. We drew that in. However, notice that as x approaches 4 in the table, the y values go to either positive or negative infinity. That's also an indication that there is a vertical asymptote at x equals 4. So the table values are proving what we see in our graph here. And so that the behavior of the f of x values is what we're really looking at. As x approaches the value of 4 from either direction, what are the y values doing? And if they approach positive or negative infinity, then that is an indication of a vertical asymptote. That is the point there for that problem. Alright, now for example 2. It says use a graphing calculator to sketch the graph of f of x equals x minus 4 over x squared minus 6x plus 8. Write the function in factor form, state the domain. So I've gone ahead and put this in the calculator and graphed it and have the graph here. So looking at this graph, we can tell that we have a vertical asymptote right in this area, and then we have a horizontal asymptote right here in this area. Alright, so it says write it in factored form. So that would be f of x equals x minus 4 already is a factor over x squared minus 6x plus 8. So we would want to multiply to 8 and add to negative 6. So that would be x minus 4 as a factor, x minus 2 as a factor. So there it is in fully factored form. Notice that even though the function is not defined at x equals 4, there is no vertical asymptote there. So looking at the graph here, x equals 1, 2, 3, 4 would be right in here. So you can tell from looking at the graph there is no vertical asymptote there. To determine the value of the function at x equals 4, create two calculator tables as x approaches 4. So x approaches 4 would be the way it's written with symbols, from the left and right. Alright, so let's do that with the calculator. Alright, so I've created these two tables as x approaches 4 from the left. This little minus sign means we're coming from the left side, and this positive here means we're coming to 4 from the right side. So approaching 4, in other words 4.1, 4.01, getting closer and closer to 4 over here from the right side, and then closer and closer to the to 4 from the left side over here. And we notice, based on the tables, what does the function value appear to be approaching as x approaches 4? Well, it's approaching 0.5 or 1/2. So a y value, an f of x value of 0.5 or 1/2. Verify this by canceling the common factor, x minus 4, and then evaluate the result at x equals 4. Sketch the graph of f of x and show a hole at x equals 4. This canceling is an indication that there is a hole in the graph. Graph the function showing the hole. Alright, so let's do all of that. So we're going to take this function up here and we're going to cancel that out. So we'll do that. Okay, now we have our originally fully factored function here, and we're going to cancel out the common factor x minus 4 in the numerator and denominator. And then it says evaluate what's left at an x value of 4. So if we do that, we would be left with 1 over x minus 2, and we want to evaluate that when x is 4, so we'll replace that x with a 4, so that would be 1 over 4 minus 2, which is 1 over 2, 1/2. So the same value that we saw the y values approaching in our table. So when that occurs, when you have factors that cancel between the numerator and denominator, that creates a hole in the graph. They do want us to resketch the graph showing a hole there at x equals 4, so we'll do that. Alright, so I've copied the graph down, so we'll put the hole in the graph at 1, 2, 3, 4, so there would be a hole right in this area. So we'll just leave an open circle. It's a little bit exaggerated. If you're sketching it, you just leave an open circle in the graph at that x value of 4 and make sure it's in the right y value too, because the hole is occurring at 4, 1/2. So that's where this open circle needs to be in your graph. Alright, in summary, for a rational function f of x, which is equal to p of x over q of x, there are discontinuities at each of the roots of q of x. So each root, so in other words, each factor in the denominator gives you a discontinuity. It is either going to be a vertical asymptote or a hole. Assuming that x minus c is a factor of q of x, so for example, before we had x minus 4 and x minus 2 as factors. If x minus c is also a factor of p of x, so it's shared between the numerator and denominator, they cancel and there's a hole there. If x minus c is not a common factor, then there's a vertical asymptote at x equals c. So in this case, we canceled at x minus 4, so we had a hole at x equals 4. We had a factor in the denominator of x minus 2 that did not cancel, and that is giving us the vertical asymptote at x equals 2. So that example had vertical asymptote from this factor and a hole from those matching factors. So that's it for this